All right, we're going to get started with part 3. So going back to this question, which I know all of you are just spending a lot of time thinking about, debating, pondering, are you sure I'm not a good free throw shooter? So in part 1, we used simulation to estimate a p-value to decide whether or not I was exaggerating about my free throw percentage. Today we're going to use a formula to find a p-value. Okay, so first of all, I want to try to write out the hypotheses. So I want you to try to write your null hypothesis and your alternative hypothesis. And when you're ready to go over those, or if you get stuck, then go ahead and hit play. Our null hypothesis here is that I truly am an 80% shooter. My claim is accurate. Our alternative hypothesis is that I am actually less than an 80% shooter. That my claim was a lie / an exaggeration. All right, so for question 2, don't worry about this. Okay. Would it be appropriate to use a normal distribution to model the sampling distribution for p hat? So for this, we have to check large counts. All right, so, and we're going to base this off of the null hypothesis, the 80%. So I'm going to do n times p and n times 1 minus p. N is 50. P is 0.8, so this would be 50 times 0.2. So I get 40 and 10. Both of these numbers are greater than or equal to 10, so yes, the sampling distribution for p hat will be approximately normal. All right, for the next one, are there any other conditions we should check? Yes, we need to check for random, and we need to check the 10% condition. For random, this is a little weird, but we're just going to assume random. I think like to get a truly random sample here, you would have to have a record of all of the free throws I've ever shot, and then you would like use a random number generator or something to select 50 of them. However, that's not super realistic, so we're just going to assume that it's random. All right, for 10% condition, 50 is less than 1/10, I'm laughing here, of all free throws I've ever taken. That's completely a lie, but we're going to go ahead and pretend that's true. Pretend I'm a big, All right, anyway. So we're going to assume that that's true. Okay, great. So those are both a little iffy, perhaps, but we're just going to go ahead and go with them. All right, so now that conditions have been met, I want you to find the mean and the standard deviation. You have these formulas in your notes. I'm going to give them to you here as well. And then I want to give you a minute to try to solve for them, okay? Cool, so when you're ready to go over those, hit play and we can check work. All right, for the mean, it's going to be 0.80 because it's just equal to our assumed population mean. And then for standard deviation, gonna plug some stuff in here. I'm gonna have 0.8 and 0.2 in the numerator and 50 in the bottom. And that's gonna give me 0.0566. All right, so we have a mean and a standard deviation now, yay. I want you to try to label the normal curve here. So what I'm asking you to do here is to label where does the mean go, where does the standard deviation go. In order to edit on Google Docs, if you click the graph, and then there's like a little edit button that pops up right down here, and then you can add text or write on the drawing. Okay, so for this, what I need to see is the mean is labeled right in the middle. And then we always label our normal curves with capital N, mean, comma, standard deviation. All right, so question here is how many standard deviations below the mean is 0.64, and then label that on the normal curve. All right, so 0.64 is going to be somewhere off this direction because it's less than 0.8. We have to figure out how many standard deviations below it'll be. So to do that, I'm going to find the z-score. So I guess I can switch, now I can see the problem. So the z-score, to find that, I'm going to find, okay, what's the difference between 0.64 and the mean? And then we divide that by the standard deviation. When you get that, it should be negative 2.82. And then I'm asking you to label that on the graph. So that's going to be like way down over here. You can't really, it's like not super, it's a very small area. But that's where our z-score is negative 2.82. Closer to the negative 3 than the negative 2 standard deviations. All right, from here, I'm going to ask you to try to find what's the probability of an 80% shooter getting at 32 out of 50 or less. There's a few ways you can do this, but I'm just going to give you a minute to work through on that. And then you can hit play when you're ready. All right, so with z-scores, you can use table A to help you find the probability, or you can also use normal CDF, which is how I'm going to show you how to do it. On normal CDF, it's going to ask you for a few things here. It's going to ask you for your lower bound, which is just negative big number. Your upper bound, which using the z-score is negative 2.82. If you're using your z-scores for the mean and standard deviation, you're going to use 0 and 1. Those should automatically pop up on your calculator when you're doing normal CDF. So you're just going to keep those as they are. The other way you could do this is using normal CDF, but using the actual proportions, not the z-score. So to do that, and you should get the same thing, or close. Our lower would still be negative huge number. But now the upper, instead of using the z-score, negative 2.82, you can use the proportion. Let's see, 32 out of 50, I don't even remember what that was. 0.64. The mean and standard deviation, you can use those from the normal curve. So the mean is 0.8, standard deviation was 0.0566. And either way we do that, whether we're using the standardized curve, which means we're using the z-scores, or we're using the normal curve with the actual values, we should be getting the same thing of 0.00. Oh, I'm answering the wrong question. Here we go, 0.002. This is our p-value. It answers the question, okay, what's the probability of getting the result we got or something even more extreme? For question 8, because 0.002 is less than 0.05, we have convincing evidence that I'm less than an 80% free throw shooter. The probability of me getting my 32 out of 50, if I was actually an 80% shooter, is so tiny. It's just this little tiny piece down here. That like, while it's still possible that I'm an 80% shooter and that I just, randomly had an off day or whatever. Yeah. However, like, the chance of that happening is so small that we're going to go ahead and we can say that we have convincing evidence that I'm less than an 80% shooter. All right, let's go over some notes here. Just a couple things I want to go over. So I want to talk about standardized test statistic, which aka z-score. And we talked about z-scores a long time ago in this class. Just a reminder, a z-score is just how many standard deviations above or below the mean. All right, so just a few things to label here. We're going to be looking at normal distributions. You're always going to want to label your mean and your standard deviation. And then I want to put those formulas that we were using up throughout the earlier part of this lesson all in one place. So to find your mean of p hat, it's just going to be equal to your null hypothesis value. To find your standard deviation for p hat, it's going to be square root p 1 minus p all over n. And then I also wanted to give you the formula for the z-score as well, in case you prefer solving things that way. So that's going to be p hat minus p, all divided by the standard deviation for p hat. And then last thing here is if your p-value is less than 5%, that means that we have statistically significant convincing evidence in your alternative hypothesis. All right, so we're going to take a moment here for the check for understanding, and then when you're ready, click play and we can go over that. Okay, so for this situation, which is sort of a weird situation, there's a bag that's filled with skunk smell. Like, how did they get that? I don't know. Okay. The null hypothesis here is that the claim is true. Sharon is claiming 90% of students can smell it. So my null hypothesis is that my proportion is equal to 0.90. My alternative hypothesis is like what we think might be happening here is that the probability is actually less than that. And the reason why we're going with less is because like we had only 84 were able to identify it. So like the question is 90% right? Or is it actually less than 90? Because our results might make us think like, maybe it is actually less than 90. And then here, just to define it, got to define your parameter. P is the true proportion of students who can identify the smell of a skunk. Cool. So for part B, why would our sample result, 84, make us think that maybe the alternative hypothesis is true? For that, our p hat based off of our sample is 84 out of 100, which is 0.84. This is less than 90. And it's just as simple as that. Because we got data that was less than what we thought was true, less than that 90%, that's some evidence. We have to decide whether it's convincing evidence, but it is some evidence. All right, so we're going to check for our conditions. There are 3 of them. We have to check for random, we have to check for 10%, and we have to check for large counts. All right, so random, let's see, it does say random sample in the problem. So we got that. All right, for 10% condition, our sample is 100. That is less than 1/10 or 10% of all students. For large counts, we have to see, would we expect to have 10 successes at least and at least 10 failures? So let's see, I've got 100. We would expect 90% of them to be able to smell the skunk, so that's 90. And then that means that we would expect 10% of them to not be able to identify it, which is 10. Both of those numbers are greater than or equal to 10, which means the large counts condition has been passed. This means we can go ahead and use a normal distribution to model. All right, so I want you to calculate the standardized test statistic, aka the z-score, and our p-value. So for this, I'm gonna always start by making a nice sketch. We have 0.9. I'm always gonna label my null value as my mean. And we have to find our standard deviation still. Okay, so in order to find that, I'm actually gonna pause for just a sec. I'll come right back, hang on.